rolling. Rolling as a rotation and a translation combined. We look at this wheel. It's rolling on the ground. The contact point is P. In this case, rolling, there's no slide. Okay. So in this case, the velocity at this point is 0. After time t, it goes to this point. Okay. And this is S. And we know if there's no sliding, this arc is equal to the S. And this S equal to r theta or theta r. And the velocity of this center of mass is ds dt. We do the ds dt, we find the velocity center of mass equal to d theta dt omega r. Rolling as a rotation and translation combined. This is a pure rotation around the center mass O, plus translation together with the center mass. Everything has the same velocity at the center mass. And these two put together, we get this one, this rolling. You see, these two velocity equal and opposite, you put together 0. This is 0, but this one is v. And those on the top both have the v, so get a 2v. So this is rolling as rotation and translation combined. The velocity of the p is 0 because no sliding, okay? And the velocity of center mass is omega r. The wheel moves smoothly, no sliding. Rolling as a pure rotation. We can look at the rolling in another angle. All the wheel rotate around this ancient axis, rotation axis at point P. Okay. It's a pure rotation with an angular speed omega about the axis, this one, okay, that always extends so point P. And turns out this angular speed omega is the same angular speed the radar observers it in pure rotation about an axis through its center mass. Let me prove it. Before we conclude, we see the kinetic energy of the rolling. Okay. It has pure rotation, so this is half IP omega prime squared. Okay, pure rotation. If it's a rotation plus translation, so that the energy is rotation energy and the translation energy. Okay. And we say this omega is equal to this omega prime. How do we do that? You see, V-com equal to R omega squared. So equal to R squared omega squared. We take the omega squared out. We're going to have I-com plus mr squared plus omega squared. What are this term? I-com plus mr squared. This is actually is IP, right? From the parallel axis, this is a inertia to the center mass, so the center mass, parallel to the axis. This is everything's concentrated on the center mass, the inertia of center mass to that axis. Okay, so we got I-com plus mr equal to IP. Then we put them to C. These are different presentation. They should be the same. So pure rotation half P omega prime equal to this one, equal to rotation and translation. And this is the IP. So we compare these two, half IP omega prime squared, half IP omega squared, they're equal. So that means omega prime and omega are the same. A rolling object has two types of kinetic energy. A rotational kinetic energy half I-com omega squared due to its rotation about its center of mass. And a translational kinetic energy half mv com squared due to translation of its center of mass. Example, a uniform solid cylinder disk is a disk of mass m 1.4 kilogram and radius r 8.5 centimeter rolls smoothly across a horizontal table at a speed 15 centimeters per second. What is its kinetic energy K? That's very simple. It's rolling, you have a two parts, okay? The omega, the angular velocity speed, equal to v com over r. Now, this is my purpose. I will do this one. V com is 15 centimeter. We have it right in standard form. Length as unit meter. So 15 centimeter is 0.15 meter per second. This is the key point in this question, okay? Yeah. So K equal to two parts, rotation part and translation part. We put everything in, you get the answer. The purpose I take this sample is this one. We have to use the standard unit. The force of rolling, friction and rolling. Rolling, you must have a friction. Okay? If the wheel rolls at constant speed and it has no tendency to slide at the point of contact P, and thus there's no frictional force acting on the wheel there. However, if a force acting on the wheel changing the speed v com of the center of the wheel or the angular speed omega above the center, then there's a tendency for the wheel to slide at P, and a frictional force acts on the wheel at P to oppose that tendency. Until the wheel actually begins to slide, the frictional force is a static friction force, Fs. If the wheel begins to slide, then the force is a kinetic friction force, Fk. Now, if some reason the wheel accelerates, it's rolling fast, then at point P on the wheel, it has tendencies to go up. So in this case, the friction opposite direct tendency goes forward. Okay, and the A com is equal to acceleration, angular acceleration, alpha r. Rolling down a ramp of ball. This is a ball. Okay. Now we set the reference. Let's set the x downward and the orange at point P. We see how describe its motion. We use Newton's second law. How many forces acting on this ball? You see the gravitational force mg, normal force we don't know, and the friction force goes this way. Okay, assume it goes this way. You can assume it goes down, whatever you like. If you do it right, you get the same physical answer. Now let's write that formula. Along x direction, I have this force, mg sine theta minus f equal to ma com. About rotation, here this rotation, you see fr equal to I alpha. Okay. Now we have 1, 2, 3 unknown, only 2 equations. That's not enough. So we need one more thing, is to find the relationship. And from this rolling, we will find out the A com equal to R alpha. Right. With these 3 equations, 3 unknown, it's very easy to solve the answer. Okay, now I just give the answer. From this one, could alpha can in terms of A, and you get an F plus F, we get an A. Okay, that's very simple one. Okay, that's a simple one. Now I want to discuss the answer. The answer is A acceleration is g sine theta over 1 plus I com over mr squared. ICOM is this one, the inertia of the center of mass. Previous we learned the sliding. Okay, we see A equal to G sine theta. Whatever mass is, it always have the same acceleration along inclined surface. But with the ruling, it's different. They have the one x term. So the A is smaller than the sliding. Okay, it's sliding. And the A depends on the icon. A different shape stuff, they have different icon. The A.
It rolls down a slope. Here are two disks of different radius and mass.
They have the same shape. Icon is the same, so they have the same acceleration.
If we roll them down this incline, they reach bottom at about the same time. Here are a disk.
This
and
time
a
they're
hoop
different
of equal
shape,
mass.
different icon.
If we roll
so they
them
have different
down the
acceleration.
incline, one will roll faster than the other. Which one will reach the bottom first? The disk rolls faster than the hoop. Here are two wooden disks of equal
They are
mass.
different shape,
One has a heavy brass
different
center
icon,
and the other
so they
a
have
heavy
different
brass rim.
velocity.
Which of these will win the race to the bottom? The disk with the heavy center wins.
This spool on an incline will be used to show what happens to a rolling body when the radius on which it is rolling is changed. When the spool is placed at the top of the incline, only the center hub is in contact with the incline. As the spool rolls down the incline, it acquires both translational and rotational velocity. What will happen to these two velocities when the spool begins to roll on the outer disks? The spool moves faster, but spins slower. Here's the action again.
This bicycle wheel has a weighted rim and an axle that can either rotate freely or can be locked to the wheel. If we put the wheel on this inclined track with the axle free to rotate, the wheel moves down with only the axle turning. If we lock the axle to the wheel so that they must turn together, how will the motion of the wheel change? The wheel now moves down the track much more slowly, but has a much larger amount of rotational energy when it reaches the bottom of the track.
This loop-the-loop track can be used to explore the relationships between energy, velocity, and centripetal force. If a ball is rolled down the track starting from just above the top of the loop, will it go around the loop? The ball falls off before reaching the top. We'll now release the ball from increasing heights.
Sample. A uniform ball of mass m 6.00 kilogram and radius r rolls smoothly from rest down a ramp at an angle theta equal 30.0 degree. Question A. The ball descends a vertical height h 1.20 meter to reach the bottom of the ramp. What is its speed at the bottom? In this case, the friction does not do any work because the point P does not move at all. Okay, so we have mechanical energy conserved. Okay, this is the final kinetic energy, final potential energy, initial kinetic energy, initial potential energy. Here, potential is the gravitational potential energy. Now we write it down. At the bottom, it has two terms. One is the rotation term, and one is the translation term. Final, we set this level UF equal to 0. And in this one, so initial potential is mgh, and initial kinetic energy is 0. So that's it. And then we have a relationship, which is Vcom equal to omega r, okay, omega r. And Icom, this is the ball. We check the table, is equal to 2mr squared over 5. We put this one inside, look at the answer. I'm not going to do it, okay? This is a 4.1 meter per second. The important thing is this one. If you know the physics, it's very easy work. Question B. What are the magnitude and the direction of the friction force on the ball as it rolls down the ramp? Before we assume the direction is going up, okay, and we have this location, RF equal to Icom alpha com, and alpha com equal to acceleration center of mass over r. What is the A? We also calculate this one. This A is special, equal to G sine theta 1 plus Icom over mr squared. In this case, it's a ball, so the Icom equal to 2mr squared over 5. And theta, we put everything in. Okay? Okay, let me see. This is theta is 30 degrees. That's it. Okay. Once we have A, we can find F. F equal Icom A equals C over r squared. Okay, and Icom equal to 2mr squared over 5. We put in r squared, cancel out. We get this one is positive. What this mean? This mean is the direction is upward, as we assume. The yo-yo is a tool when we were kids, we play, give us so much fun. Okay, let's look at the free body diagram. The rams wrapped at the axis, small axis, are 0, very tight. And outside we have two big discs on two ends to increase the initial. And look at this free diagram. Fmg minus t equal to ma, and rotation t r0 equal to I alpha, and alpha A has relationship Acom equal to R0 alpha, this is R0, okay? And these three, it's very easy, we get A. Now, this A is similar to the A we rolling down the road, the incline. You look at this one, when Icom is very large, and this is large, the Acom is smaller. When R0 is very small, this turn is large, the A is small. This is what we want, okay? We want it is a very large Icom, very large, the disc on both sides, and very small radius R0.
This device works like a yo-yo turned inside out. When we wind it up along the string, we store gravitational potential energy. After it is released, that energy is gradually transformed into rotational energy of the disk. When the disc reaches the bottom of the string, it begins to roll back up. The rotational energy is gradually transformed back into gravitational potential energy. When the